Welcome to the API Testing Interview Challenge Series, your complete bootcamp to mastering API testing, automation, and interview readiness. Across 20 progressive challenges, we'll move step by step, from the basics all the way to enterprise-level, capstone projects. Here's how the journey unfolds: Part 1, the foundation, challenges 1 to 5. You'll start with the essentials: gets, posts, chaining APIs, authentication, and validating responses. This builds your foundation. Part 2, core automation, challenges 6 to 10. Tackle data-driven testing, error handling, schema validation, and environment setups, the skills that interviewers expect every automation tester to know. Part 3, advanced engineering, challenges 11 to 16. Then we go deeper, advanced topics like OAuth, mocking APIs, performance baselines, reporting, and working with external data sources. This is where you move from a tester to an automation engineer. Part 4, the capstone, challenges 17 to 20. Finally, the capstone, full end-to-end business workflows, building your own API automation framework, integrating into CI/CD pipelines, and even security testing with SQL injection and fuzzing. This is the grand finale that mirrors real enterprise projects. By the end of this series, you'll not only have practiced every major API testing interview scenario, but you'll also have the mindset, frameworks, and end-to-end skills that make you stand out as an automation architect. This isn't just about answering questions, it's about proving you can think, design, and deliver automation like a professional. Let's get started with Challenge 1. Part 1, the foundation, challenges 1 to 5. Welcome to Part 1 of our API Testing Interview Challenge series. In this first stage, we'll build your foundation. You'll start with the essentials: sending GET and POST requests, chaining API calls together, handling query parameters and headers, and performing your first validations. These challenges are designed to give you confidence with the basics, the skills every API tester must demonstrate in an interview. By the end of Part 1, you'll be comfortable exploring APIs, verifying responses, and writing simple but effective test cases. Let's begin by mastering the building blocks. API Testing Challenge 1, your first GET request. The interview task: test a simple GET endpoint. An interviewer starts with a warm-up. Your first task is to test a public health check endpoint, https://api.publicapis.org or health. Using Postman, please write tests to verify 2 fundamental things: first, that the API returns a 200 OK status code, and second, that the response time is acceptably fast, let's say under 500 milliseconds. Let's solve this step by step. The visual anchor, the basic API test flow. This is the most fundamental API test, the heartbeat check. We send a GET request from our client, Postman, to the API server. We aren't concerned with the data in the response body yet. We are only focused on the metadata of the response. Did we get a 200 OK status back, confirming the server is healthy? And second, did it respond quickly? This simple check forms the foundation of all API testing. Step-by-step solution: Postman test script. Disclaimer: always test code in a non-production environment. This is the standard structure for a Postman test. pm.test parentheses is a function that defines a test case. The first argument is a descriptive name that will appear in the test results. Inside the function, pm.response.to.have.status, 200, is the assertion. It checks if the response object from the API call has a status code of exactly 200. For our second test, we check performance. pm.response.responseTime is a built-in Postman variable that holds the response time in milliseconds. We use the pm.expect parentheses assertion style, which is common in JavaScript testing, to verify that this value is less than the 500 milliseconds threshold required by the interviewer. Question: follow-up question 1, what are some other common status codes you might expect or test for on a health check endpoint? Answer: besides 200 OK, a health check might be designed to return 204 no content if it is successful but has no body to return. For negative testing, I would check 4503 service unavailable to see how the API behaves when its downstream dependencies are down. Testing for these edge cases demonstrates a more thorough approach. Question. Follow-up question 2. Why is testing response time important even in a simple functional test like this? Answer. It is a form of early performance regression testing. An API that is functionally correct but takes 5 seconds to respond is effectively broken from a user's perspective. By including a basic response time check in our functional test suite, we can catch performance degradations with every code change, long before they become a major issue in production. Question. Follow-up question 3. Curveball. This is a public API. In a real-world private API, what's the most common HTTP header you would need to add to this request for it to succeed? Answer. In a real-world scenario, I would almost certainly need an authorization header. Typically, this would be in the format authorization, bearer JWT underscore or underscore auth underscore token. Alternatively, for simpler machine-to-machine APIs, I might need to provide an API key in a header like XAPI key, my secret key. This shows I'm thinking ahead about security, which is a critical part of API testing. What the interviewer is really looking for. Core Postman skills. Do you know how to navigate to the Tests tab and write basic JavaScript assertions? HTTP fundamentals. Do you understand the meaning of A200OK status code and why it is the primary indicator of success? Assertion syntax. Can you use the built-in Postman snippets, pm.response, and the chai.js syntax, pm.expect, to validate response properties? Beyond functionality, do you think about non-functional requirements like performance, even at a basic level? Your turn. Extension. Now, add a third test to this request. The response body of the health check is alive, true. Write a test to verify that the response is valid JSON and that the alive property has a Boolean value of true. Hint. You will need to parse the response body using const JSON data equals pm.response.json parentheses. API Testing Challenge 2, the JSON response validation. The interview task, validate the content of a JSON response. The interviewer continues, great, the health check passed. Now, let's test a core endpoint, https://johnplaceholder.typico.com or users/1. I need you to write Postman tests that go beyond the status code. Please verify the content of the JSON response, confirm the user's ID is 1, their name is Leanne Graham, and that the email field contains a valid symbol. Let's break it down. The visual anchor, deconstructing the JSON response. This diagram shows how we shift our focus from just the response metadata to the content inside. The test unboxes the JSON payload, allowing us to target and validate specific key-value pairs. This is the essence of content validation and proves the API is returning the correct data. Step-by-step solution, Postman test script. Disclaimer, always test code in a non-production environment. This is the most critical first step for content validation. pm.response.json parentheses is a Postman function that takes the raw text response body and automatically parses it into a JavaScript object that we can easily work with. We store this object in a variable called responseBody. Now that we have a JavaScript object, we can access its properties using dot notation. We access responseBody.id and use pm.expect parentheses to assert that its value is equal to 1. We use dot to dot equal parentheses for a robust equality check. Similarly, we access the name property with responseBody.name and assert that it is equal to the exact string Leanne Graham. This confirms the API is returning the correct data for user 1. For the email, we perform a basic structural check. Instead of asserting the full email address, which might change, we check that the string responseBody.email includes the character. This is a simple but effective way to validate the format without making the test too brittle. Follow-up question 1. Your test for the user's name is very specific. What if the name changes? Is there a more resilient way to write this test? Answer: absolutely. For data that might change, asserting an exact value can make tests brittle. A more resilient approach is to validate the contract, the structure and data type. I would change the test to assert the presence and type of the field, like this: pm.expect, response body, .to .of.property, name, .that is string. This test still passes if the name changes, but it will fail if the name key is removed or returns a number, which is what we really care about. Follow-up question 2, your email check is quite basic. How would you perform a more rigorous validation of the email format? Answer: for a more rigorous check, I would use a regular expression, regex. I could define a standard regex pattern for email validation and then use a JavaScript assertion to check if the email string matches that pattern. For example, const email regex equals // s plus at /s plus /s plus / pm.expect, response body.email, to match, email regex. This is much more precise and reliable than simply checking for an @ symbol. Follow-up question 3, curveball: what if the endpoint was /users and it returned a large array of 100 users? How would you efficiently verify that every user in the array has a valid ID? Answer: I would iterate through the array. After parsing the JSON, I would use a for each loop on the response body array. Inside the loop, I can write assertions for each user object. To get detailed feedback, I can even create dynamic tests: response body.forEach, user equals, pm.test, user $user.id, has a valid ID, equals, pm.expect, user.id, to b.a, number. This ensures the entire dataset adheres to the contract, not just the first element. What the interviewer is really looking for. JSON parsing: can you correctly use pm.response.json parentheses to work with the response body? Property access: do you know how to use notation, response body.name, to access JSON properties? Data-specific assertions: can you write precise tests that validate the values and types of different fields, numbers, strings? Resilience thinking: do you understand the trade-off between strict value checking and more flexible contract testing, checking for presence and type? Your turn, extension. The user object in the response contains a nested address object, which in turn has a geo object with lat and lng properties. Write a new test to validate that the address.geo.lat property exists and is a string. This will test your ability to traverse nested JSON structures. API Testing Challenge 3, Chaining Requests with Variables. The interview task: create a dynamic test workflow. The interviewer now tests your ability to handle dependent requests. Let's build a simple user workflow. First, send a GET request to https://johnplaceholder.typico.com or users to get a list of all users. From that list, I want you to capture the ID of the first user. Then, in a second request, use that captured ID to fetch all the posts for that specific user from the /posts endpoint. Your tests should confirm that the second request was successful and that all returned posts belong to the correct user. The visual anchor, the dynamic data flow. Here we see a critical API testing skill, capturing dynamic data from one response and injecting it into the next request. This creates a realistic test workflow that mimics how real applications work, for example, a login request that returns a token, which is then used to access a user's profile. Mastering this flow is essential for any end-to-end testing. Step-by-step solution, Postman. Disclaimer: always test code in a non-production environment. Our workflow starts with the first request, a simple GET call to the /users endpoint to fetch a list of all available users. In the Tests tab for request 1, our very first line of code is to parse the raw JSON response into a usable JavaScript object. Next, we access the first user in the returned array using index 0, and then grab their ID property using notation. This is the core of the chaining technique. We use pm.environment.set parentheses to store the first user ID in a variable named captured_user_ID. We add a simple test to confirm that a valid, non-null ID was actually captured before the collection runner proceeds to the next request. Now we define our second request. In the URL, we use Postman's variable syntax, captured_user_ID, to dynamically inject the ID we just saved. In the Tests tab for request 2, we again parse its response and also retrieve the stored user ID from the environment so we can use it for our assertions. We start the validation with an essential test to confirm that this second API call was successful by checking for a 200 OK status code. This final test proves the entire chain worked. We loop through every post returned by the API and assert that its user ID property matches the ID we captured from the first call. We use parseInt parentheses because environment variables are always stored as strings. Follow-up question 1. What is the difference between collection, environment, and global variables in Postman? Answer. Global variables are for general-purpose values that rarely change, like ABASEURL. Collection variables are scoped to a single collection and are good for values specific to that set of requests. Environment variables are for values that change depending on the environment you are testing against, for example, dev, staging, prod. For dynamic data like auth tokens or captured IDs, environment variables are the standard choice. Follow-up question 2. Why are environment variables better than global variables for captured IDs in a CI/CD pipeline? Answer. This is a critical distinction for automation. Environment variables allow you to isolate test data and state for each test run. In a CI/CD pipeline, you might run tests against staging and UAT environments simultaneously. By using separate environment files, you ensure the captured_user_ID from the staging run does not leak and corrupt the UAT run. Global variables are a single, shared state, which can cause test flakiness and conflicts in parallel or multi-environment runs. Follow-up question 3. Curveball. Your current test always picks the first user. How would you modify the first script to pick a random user from the response array instead? Answer. Would use JavaScript's built-in math functions. After parsing the response body array, I would get a random index like this. Const random index equals math.floor, math.random parentheses asterisk response body.length. Then, I would get the user at that index, const random user equals response body, random index. Finally, I would set the environment variable with randomuser.id. This makes the test less predictable and better at catching edge cases. What the interviewer is really looking for. Dynamic workflow logic. Can you think beyond a single request and design a multi-step test flow? Variable management. Do you understand how to use variables, pm.environment.set and, to pass data between requests? Automation mindset. Do you understand variable scoping, environment versus global, and its importance for reliable CI/CD runs? Robust assertions. Can you write a test, the for each loop, that validates an entire dataset, not just a single value? Your turn, extension. Extend this workflow by adding a third request. After fetching the posts for a user, capture the ID of the first post from that response. Then, make a third API call to get /comments, post ID equals captured_post_ID to fetch the comments for that specific post. Your final test should verify that the comments belong to the correct post ID. API Testing Challenge 4, Creating a User with Post. The interview task, create a new resource via a post request. The interviewer shifts from reading data to creating it. Now let's test a write operation. I need you to send a post request to https://johnplaceholder.typico.com or users to create a new user. Your request must include a JSON body with a name, username, and email, and make sure you include the necessary headers to tell the server what kind of data you are sending. After sending the request, write tests to validate that the API responds with a 201 created status and that the user data in the response body matches the data you sent. The visual anchor, constructing and sending the post request. This flow visualizes the key components of a post request. The client constructs a JSON package, the payload, and sets the correct headers to describe its content. The server's successful response, 201 created, confirms the new resource has been created. Crucially, it returns the created object, allowing for echo validation, where we confirm the returned data matches what we sent, including any new server-generated fields like an ID. Step-by-step solution, Postman setup and test script. Disclaimer: always test code in a non-production environment. In our test script, this is a powerful technique. We retrieve the raw text of the request body we just sent, pm.request.body.raw, and parse it into a JavaScript object. This allows us to dynamically compare what we sent with what we received. This is the primary assertion for a create operation. We check specifically for a 201 created status, not 200 OK. This confirms that a new resource was successfully created as a result of our request. A robust test checks headers, not just the body. This assertion verifies that the server correctly identifies its response as JSON, which is a key part of the API contract. This is a core echo validation test. We are checking if the server correctly processed and stored the data we sent. We assert that the name and username fields in the response are equal to the corresponding fields from the request body we defined earlier. When a new resource is created, the server typically generates a unique ID. This test validates that the response body contains an ID property and that its value is a number, confirming the creation was successful and the resource is now addressable. Follow-up question 1. What's the key difference between a 200 OK and a 201 created status code? Answer: 200 OK is a generic success status for many operations, typically for successful GET requests. 201 created is a more specific success code used exclusively when a post or put request successfully creates a new resource on the server. It explicitly confirms creation. Follow-up question 2. What would likely happen if you forgot to set the content type header to application or JSON? Answer: the server would not know how to interpret the request body. It might default to treating it as plain text or form data, which would fail parsing. This would likely result in a 400 bad request or 415 unsupported media type error, as the server cannot process the payload in the format it was received. Follow-up question 3. What if you had to create 100 unique users? Would you just copy and paste this request 100 times? Answer: absolutely not. That would be inefficient and unmaintainable. The correct approach is data-driven testing. I would create a CSV or JSON file with 100 rows of user data. Then, using Postman's collection runner or Newman, I would iterate through the data file, running this same request once for each row and substituting the data dynamically. This is a far more scalable and professional approach. Follow-up question 4. Curveball: the API response includes an ID. How would you modify this test to immediately delete the user you just created, ensuring your test cleans up after itself? Answer: that's a great question about creating self-contained, non-destructive tests. In the Tests tab of this post request, I would capture the new ID, const new user ID equals responsebody.id, and save it to an environment variable, pm.environment.set, newly_created_user_id, new user ID. Then, I would create a second request in my collection, delete/users/newly_created_user_id. In the collection runner, I would order them so the delete runs right after the post, ensuring my test data is cleaned up after every run. What the interviewer is really looking for. HTTP method knowledge: do you know that POST is the standard method for creating new resources? Request construction: can you correctly build a request with both a JSON body and the necessary headers, content type? Status code specificity: do you understand the semantic difference between 201 created and 200 OK? Payload validation: can you write tests to confirm that the API correctly processed and echoed back the data you sent? Data lifecycle awareness: do you think about the full lifecycle of test data, creation to validation to cleanup, especially in automated CI/CD pipelines? Your turn, extension. The API at https://johnplaceholder.typico.com or posts allows you to create new posts. Create a new post request to this endpoint with a title, body, and user ID. Write tests to verify the 201 created status and confirm the title and user ID were echoed back correctly. As a bonus, create a second, negative test. Try sending the request without the title field and assert that the API returns an appropriate error status code, like 400 or 500.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
API Testing Challenge 5, Login and Token Handling. The interview task, test a complete user authentication flow. The interviewer presents the most common scenario in API testing. This is the classic flow. First, you need to post a user's credentials to /auth or login to get an authentication token. Then, you must use that token as a bearer token in the authorization header of a second request to get the user's data from a protected /users or profile endpoint. Your tests must prove that a token is successfully captured and used to access the protected data. Conversely, the test should fail with a 401 unauthorized error if the token is missing or invalid. The visual anchor, the token authentication workflow. This diagram illustrates the fundamental pattern of token-based authentication. The client exchanges credentials for a temporary, secure token, a key. This key is then stored and presented in the header of subsequent requests to unlock protected resources. This stateless approach is the foundation of modern API security. Mastering this flow is non-negotiable for an API tester. Step-by-step solution, Postman. Disclaimer: always test code in a non-production environment. The flow starts with a post request to the login endpoint, providing the user's credentials in the JSON body to exchange them for a token. In the Tests tab, we parse the response, capture the token property, and immediately store it in an environment variable named auth_token. This makes it available for all subsequent requests. We validate that the login was successful, 200 OK, and, crucially, that the token we received is a non-empty string. This confirms the first part of the flow worked as expected. For the second request, we use Postman's authorization helper. By selecting bearer token and inserting our auth_token, a variable, we ensure Postman constructs the authorization bearer token header correctly for us. This test is the ultimate proof that our token was valid. A 200 OK status means the server accepted our token and granted us access. A missing or invalid token would have resulted in a 401 unauthorized error. Finally, we validate the response payload to confirm we received the correct data for the authenticated user, completing the end-to-end test of the authentication and authorization flow. Follow-up question 1. What exactly is a bearer token? Answer: a bearer token is a type of access token. The name bearer means that whoever possesses, that is, bears, the token is granted access. It is a self-contained credential, and the server just needs to verify its signature is valid and it has not expired. It is sent in the authorization header like this: authorization, bearer, the token string. Follow-up question 2. How would you scale this test to simulate 50 different users logging in? Answer: would use data-driven testing. I would create a CSV file with 50 rows, each containing a unique email and password. In the Postman collection runner, I would select this file and set the iteration count to 50. Postman would then execute this login and fetch flow for each user, ensuring the entire authentication system is robust at scale. Follow-up question 3. Curveball: what happens if this token expires midway through a long test run? How could you design a test collection to be resilient to that? Answer: that's a fantastic question about building robust automation. I would design a shared, reusable login request. Then, for any request that fails with a 401 unauthorized status, I would use logic in its test script to trigger the login request again using postman.setNextRequest, login request. The login request would then redirect back to the originally failed request. This creates an automated re-authentication loop, making the entire test suite self-healing. What the interviewer is really looking for. Authentication concepts: do you understand the purpose and mechanism of bearer token authentication? Stateful testing: can you manage state, the token, across multiple, dependent API calls? Tool proficiency: do you know how to use Postman-specific features like the authorization tab and environment variables effectively? Security awareness: do you understand the sensitivity of tokens and why they should not be hard-coded, committed to Git, or logged in plain text? Resilience and automation design: can you think ahead about real-world problems like token expiration and how to handle them programmatically? Your turn, extension. Extend this flow to test a write operation on a protected route. Add a third request, a put to /users or profile with a body like location, New York. Use the same auth_token for authorization and test for a 200 OK status. As a bonus, duplicate this third request, remove the authorization, and add a new test to assert that the server correctly returns a 401 unauthorized status. Real-world capstone angle. This login capture use pattern is the absolute foundation for testing almost every modern, secure web application, from social media platforms and e-commerce sites, and is the backbone for secure microservice-to-microservice communication using standards like JWTs and enterprise systems. Transition, Part 1 to Part 2, from Basics to Intermediate. You've now built a strong foundation with the basics of API testing. But interviews don't stop at just gets and posts. In Part 2, we'll level up. You'll learn data-driven testing, error handling, schema validation, and environment management. These are the exact scenarios where many candidates stumble, but you'll turn them into your strengths. Let's move into the intermediate stage and expand your toolkit. Part 2, Intermediate Mastery, Challenges 6 to 10. Welcome to Part 2 of the series. Here, we'll tackle the real-world skills that separate beginners from professionals. You'll learn how to handle dynamic data, validate complex responses with schemas, manage test environments and variables, and even explore error and negative testing. By the end of this section, you won't just be sending requests, you'll be designing tests that are reusable, maintainable, and interview-ready. API Testing Challenge 6, Data-Driven Testing with a CSV. The interview task: scale your tests with an external dataset. The interviewer is impressed with your single-user login test and wants to see if you can scale it. That's great for one user, but we need to test many scenarios. I have a CSV file with 3 user credentials, one is valid, one has a wrong password, and one is for a locked-out account. I need you to use Postman's collection runner to execute our login test against all 3 rows in this data file in a single run. Your tests should be dynamic enough to validate both success and failure based on the data provided. The visual anchor, the data-driven testing loop. This diagram visualizes the data-driven testing workflow as a clear, 3-part process. On the left, the login_data.csv file acts as our input source, containing multiple rows of user data for both success and failure scenarios. An arrow labeled Iterate shows these rows being fed one by one into the central engine, the Postman collection runner. Inside, a generic post/login request uses variables like username as placeholders. The final output on the right is the test report. Critically, it shows a white heavy checkmark passed result for both the valid and invalid user, because the tests correctly verified the expected outcome for each row. Step-by-step solution, data file plus Postman script. Disclaimer, always test code in a non-production environment. First, we create our data source. This CSV file has headers that will become variable names. Crucially, we include not just inputs, username, password, but also the expected outcome, expected status code, and a descriptive test case name for better reporting. Next, we modify our request body. We replace the hard-coded email and password with Postman's variable syntax, username, and password. When the collection runner executes, it will substitute these placeholders with values from the corresponding column in the CSV for each iteration. In our test script, we use pm.iterationData.get to read data from the current row of the CSV. We must use parseInt parentheses because data from CSV files is always read as a string, but the status code is a number. This is the core of our dynamic test. It asserts that the actual response code matches the expected code from our CSV. This single test elegantly handles both success, 200, and failure cases, 401, 403, making our script concise and powerful. This conditional block shows advanced scripting. We only attempt to parse the JSON and check for a token if the login was actually successful, status code 200. This prevents our tests from failing on error responses that do not have a JSON body, making the test report cleaner. Follow-up question 1. What is the difference between pm.iterationData and pm.environment variables? Answer. pm.iterationData contains data from an external file, CSV or JSON, and is only available within the context of a collection runner or Newman run. Its scope is a single iteration. pm.environment variables are more persistent. They are set for a specific environment and can be read and written to across multiple requests within that run. You would use iteration data for inputs and environment variables for chained values like auth tokens. Follow-up question 2. This is great in the Postman app, but how would you run these data-driven tests in a CI/CD pipeline like Jenkins? Answer. For CI/CD, I would use Newman, which is Postman's command line collection runner. The command would look something like this: Newman run my_collection.json staging.postman_environment.json dlogin_data.csv. This allows the exact same data-driven tests to be executed automatically in the pipeline, with the results published to the build logs. Follow-up question 3. Curveball: your CSV contains sensitive passwords in plain text. What are the risks, and what's a more secure way to handle this? Answer. The risk is that anyone with access to the repository can see user passwords, which is a major security flaw. A more secure approach is to not store passwords in the data file. Instead, you could store a token for a preceded test user in a secrets management system, like HashiCorp Vault or AWS Secrets Manager. The CI/CD pipeline would fetch this secret at runtime and inject it as an environment variable, which the test script can then use. This way, no sensitive data is ever committed to the codebase. What the interviewer is really looking for. Scalability mindset: do you think beyond single, manual tests and towards automated, high-coverage scenarios? Efficiency and DRY principle: Can you write one generic test that handles multiple data sets instead of duplicating tests? Data literacy. Can you structure an external data file effectively, including not just inputs but also expected outputs? Automation maturity. Do you know about command line tools like Newman and how they enable CI/CD integration? Robustness. Do you instinctively test for both positive, happy path, and negative, error path, conditions? Your turn, extension. Take the create user post request from challenge 4 and make it data-driven. Create a CSV file named user_creation_data.csv with columns for name, username, email, and expected status code. Include one row for a successful creation, expect 201, and a second row with an invalid email format, for example, bad email, and expect a 400 bad request status. Modify the request and test script to run using this data file. API Testing Challenge 7, Schema Validation. The interview task, validate the API's structural contract. The interviewer now wants to test your understanding of contract testing. Manually checking individual fields like name and email is brittle and does not scale. If 10 new fields are added, our tests become a nightmare to maintain. Instead, I want you to validate the entire structure of the user object from get https://johnplaceholder.typico.com/users/1. Define a JSON schema that represents the user contract, and use Postman to assert that the API response conforms to it. The test should pass only if all required fields are present with the correct data types. The visual anchor, blueprint versus building validation. This diagram illustrates the powerful concept of schema validation using a clear, blueprint versus building analogy. On the left, we see the blueprint, represented by an architectural drawing icon. This is our JSON schema, the official plan that strictly defines what the API response should look like, including required fields and their correct data types. On the right, we have the building, represented by a code icon. This is the actual API response that the server sends back, the finished structure that we need to inspect. Both the blueprint, the rules, and the building, the result, are fed into the central validator engine. This engine, represented by the gear and magnifying glass, symbolizes the automated process run by tools like Postman's built-in validator, which uses AJV. At the bottom, the validator produces a single, unambiguous verdict. It outputs either a green checkmark indicating schema valid if the API response perfectly matches the blueprint, or a red cross indicating schema invalid if there is any structural mismatch. This visual story shows how schema validation provides one comprehensive pass/fail result for the entire data structure, making it a far more efficient and reliable testing method than checking dozens of individual fields manually. Step-by-step solution, Postman test script. Disclaimer: always test code in a non-production environment. First, we define our contract as a JavaScript object that follows the JSON schema specification. We declare the top-level type is an object, list its properties with their expected types, and provide an array of required fields. This single object is our source of truth for the user structure. Our entire test case is now incredibly concise and readable. We define a test named response body conforms to the user schema. Inside, we parse the response and then run our single, powerful validation check. This is the core of the solution. The .to.have.json schema parentheses is Postman's built-in assertion that takes the entire response body object and compares it against our user schema contract. It automatically checks for property presence, data types, and nested structures, failing the test if there is any mismatch. Follow-up question 1. Why is this method superior to manually checking each field like we did in Challenge 2? Answer: it is superior for three main reasons. 1. Maintainability. If the API contract for a user changes, for example, adds 5 new fields, I only need to update the schema in one place, not 5 new test assertions. 2. Robustness. It checks the entire structure, not just the fields I remember to test. It will automatically catch unexpected type changes, for example, an ID changing from a number to a string. 3. Clarity. It separates the definition of the data, the schema, from the execution of the test, making the test's intent. Does this match the contract? Much clearer. Follow-up question 2. What happens if the API adds a new, non-required field to the response, like phone? Will this test fail? Answer: no, by default, it will not fail. The standard JSON schema specification allows for additional properties. If we wanted to enforce a strict contract and fail the test on any unexpected fields, we would add additional properties, false at the relevant object level in our schema. This is a critical strategic decision based on whether the API should be extensible or strictly defined. Follow-up question 3. Curveball: the backend API for this user service is not built yet, but the team has given you this exact JSON schema from their OpenAPI specification. How can you use it to start testing today? Answer: this is a perfect scenario for shift-left testing using a mock server. I can take that JSON schema and use it in Postman to create a mock server. Postman will automatically generate example responses that conform to the schema. I can then write and run my entire suite of tests against this mock server. When the real API is deployed, I only need to change the base URL, and all my tests should work, validating that the developers built the API according to the agreed-upon contract. What the interviewer is really looking for. Contract-first mindset. Do you think of an API structure as a formal contract that needs to be enforced? Efficiency and scalability. Do you understand this is a more efficient and maintainable way to validate complex objects than writing dozens of individual assertions? Knowledge of JSON schema. Do you know the basic syntax and purpose of key fields like type, properties, and required? Proactive testing strategy. Do you think about how to test an API before it is even built, using mocks and schemas? Attention to detail. Do you consider edge cases like new fields being added, additional properties? Your turn. Extension. The user object in the response from get/users/1 also contains a nested company object. Update your user schema to include validation for this company object. It should be a required property of the main object, and it must contain 2 required string properties, name and catchphrase. API Testing Challenge 8, Error Handling and Negative Testing. The interview task: test the API's unhappy paths. An interviewer wants to see how you handle failure. Happy path testing is easy. I need you to prove our API is robust by testing its error handling. Please write 3 separate tests to validate the following scenarios. 1. A 401 unauthorized error when accessing a protected route with an invalid token. 2. A 404 not found error when requesting a resource that does not exist. 3. A generic 500 internal server error response from a known buggy endpoint. The visual anchor, the happy path versus the error paths. This diagram visualizes error handling and negative testing as a journey with multiple, distinct routes. On the far left, a single client acts as the starting point for all test scenarios. From this client, the request path immediately branches to represent 4 different test cases. The top green path, labeled Valid Request, represents the happy path, the ideal scenario. Below it, the 3 red paths represent the unhappy paths or negative tests. Each is labeled with a specific error condition we are simulating: an invalid token, a request for an unknown ID, and a buggy request designed to cause a server failure. Crucially, all 4 paths lead to a single, consolidated outcomes box on the right. This box clearly maps each request path to its predictable result. The valid request yields a 200 OK, while the negative tests correctly result in their expected error codes like 401 unauthorized, 404 not found, and 500 server error. This visual proves that a robust API is one where every path, good or bad, leads to a known and verifiable destination. Step-by-step solution: Postman test scenarios, using JavaScript. Disclaimer: always test code in a non-production environment. For our first test case, we intentionally send an invalid token. This test asserts that the response status is exactly 401, confirming the API's security correctly rejects the request. Following the 401 status check, we also validate the error message. We parse the JSON response and assert that the error property contains the expected text. Note, the structure of error responses can vary, so this test should be adapted to match your specific API. To test for A404, we request a user with an ID that is highly unlikely to exist. The entire test consists of this single assertion, which passes if the server correctly responds that the resource was not found. For the server error test, we target a hypothetical endpoint designed to fail. The first test validates that the status code is exactly 500, confirming a server-side error was triggered. Finally, we check the body of the 500 error response. Since server errors might not return valid JSON, we safely check the raw text of the response to ensure it contains a user-friendly error message. Follow-up question 1. Why is negative testing just as important as positive testing? Answer. Positive testing verifies that the system works under ideal conditions, but negative testing ensures the system is robust and secure. It confirms the application can handle unexpected inputs and failures gracefully without crashing or exposing vulnerabilities. In the real world, users make mistakes and systems fail, so testing these unhappy paths is critical for building a reliable product. Follow-up question 2. Why is it important for an API to return specific error codes like 401 or 404, instead of just a generic 400 error for everything? Answer. Specific error codes are crucial for several reasons. For client applications, it allows them to react intelligently. For example, a 401 can trigger a redirect to a login page, while a 404 can display a "not found" message. For debugging and monitoring, specific codes immediately tell developers where to look for the problem. For example, for XX is a client issue, 5XX is a server issue, which drastically speeds up troubleshooting. Follow-up question 3. What is the difference between a 401 unauthorized and a 403 forbidden error? Answer. A 401 unauthorized means, I do not know who you are. You are completely unauthenticated. A 403 forbidden means, I know who you are, but you are not allowed to access this. You are authenticated, but your user role does not grant you the required permissions for that specific resource. Follow-up question 4. Curveball. How would you automate testing for a rare, intermittent 503 service unavailable error that only happens during peak server load? Answer. I would combine functional and performance testing. I would use a tool like K6 or JMeter to generate a high load on the server. Simultaneously, I would run a monitoring test using Newman in a continuous loop. This test would hit the service endpoint, expecting a 200 OK, but would log a critical failure if it ever receives a 503. This combination of load generation and constant monitoring is the best way to catch and validate such intermittent, load-dependent errors. What the interviewer is really looking for. Robustness mindset. Do you instinctively think about how the system should behave when things go wrong? HTTP status code mastery. Do you know the precise meaning of different error codes, for XX for client errors, 5XX for server errors? Edge case identification. Can you identify and design tests for scenarios beyond the happy path? Systematic approach. Can you create distinct, focused tests for different types of errors rather than lumping them all together? Your turn. Extension. A common client-side error is 400 bad request. Using the post/users endpoint from challenge 4, create a new request with a deliberately broken JSON payload, for example, with a missing comma. Write a test that asserts the API correctly responds with a 400 status code. As a bonus, also assert that the response body contains an appropriate error message, such as malformed JSON or invalid input. API testing challenge 9, parameterized requests. The interview task, fetch specific and filtered data. The interviewer wants to check your understanding of how to structure URLs to retrieve data. I have 2 scenarios for you. First, I need you to fetch a single, specific user by their ID using a path parameter, for example, user with ID 5. Second, I want you to fetch all the posts written by that same user, using a query parameter to filter the results. For both requests, you must write tests to validate that you received the correct data. The visual anchor, the URL's two types of parameters. This diagram uses a side-by-side comparison to explain the two types of URL parameters. The panel on the left describes a path parameter. It is defined as the unique address of a resource. The example syntax shows users user ID, which results in a single JSON object for that specific user. The panel on the right describes a query parameter. It is defined as instructions to filter or sort a collection of resources. The example syntax shows /posts user ID equals 5, starting with a question mark, which results in a JSON array containing all items that match the filter. This visual directly contrasts how a path parameter is used to identify a single, specific resource, while a query parameter is used to operate on a larger collection of resources. Step-by-step solution, Postman scenarios, using JavaScript. Disclaimer: always test code in a non-production environment. For the first scenario, we use a path parameter to identify a unique resource. In Postman, we use the variable name syntax in the URL and then define its value, 5, in the dedicated path variables section below. Our tests for the path parameter are now more robust. We verify that the response is a single JSON object and that its ID matches the user ID we specified in the path, confirming we got the correct user. For the second scenario, we use a query parameter to filter a collection. The best practice in Postman is to use the params tab. We add a key user ID and a value 5, and Postman correctly appends user ID equals 5 to the URL for us. This robust test validates the filter. After first confirming the response is a non-empty array, we loop through every post in that array and assert that its user ID property matches the ID from the query parameter. This proves the filter worked correctly across the entire dataset. Follow-up question 1, in simple terms, what's the main difference between a path parameter and a query parameter? Answer: a path parameter identifies a specific, unique resource, for example, /users/5 gets you exactly one user. A query parameter is used to filter, sort, or paginate a collection of resources, for example, /posts user ID equals 5 gets you a list of posts that meet a certain criteria. Follow-up question 2, what happens if you use both a path parameter and a query parameter that seem to conflict, like get /users/5 user ID equals 6? Answer: this is a great question about API design. A well-designed REST API will almost always give precedence to the path parameter, as it defines the primary resource being requested. In this case, the API should return user with ID 5 and simply ignore the conflicting user ID equals 6 query parameter. The path is the identifier, the query is just a filter on the result. Follow-up question 3, curveball: how would you structure a single request to get the second page of posts for user 5, assuming 10 posts per page? Answer: would combine multiple query parameters. The request would look like this: get /posts user ID equals 5 and _page equals 2 and _limit equals 10. Here, we are chaining 3 separate query parameters using the n symbol to filter by user, select the page number, and set the page size, all in one efficient request. What the interviewer is really looking for. URL structure knowledge: do you fundamentally understand the components of a RESTful URL? Semantic distinction: can you clearly articulate the difference in purpose between path and query parameters? Tool proficiency: do you know how to use Postman's dedicated UI features for managing both types of parameters? Robust validation: can you write comprehensive tests that prove the parameters are working correctly, for example, looping through a filtered list? Your turn, extension. The API at https://json placeholder.typico.com/album supports filtering by user ID. Write a request that uses a query parameter to fetch all albums for user ID 1. Your test script should verify that 1. The response status is 200, 2. The response body is an array with more than 0 items, and 3. Every album in the array has the correct user ID and contains a title property that is a non-empty string.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
API Testing Challenge 10, the CRUD Cycle Challenge. The interview task: test the full life cycle of a resource. The interviewer wants to see you connect everything together in an end-to-end flow. This is a comprehensive test. I need you to write a sequence of requests in Postman that performs a full CRUD cycle on a blog post. You must 1. Create a new post using post-to/posts. 2. Read that same post using get and its new ID to verify it was created correctly. 3. Update the post using put with a new title. 4. Delete the post using delete. As a final step, prove that the post is truly gone by trying to get it again and asserting that you receive a 404 not found error. The visual anchor: the life cycle of a resource. This diagram visualizes the full CRUD cycle as a color-coded, clockwise life cycle of a resource. The cycle begins at the top with step 1, create, represented by a green segment and a post request. The flow continues clockwise through step 2, read, blue, get, step 3, update, orange, put, and step 4, delete, red, delete, showing how the resource is first created, then verified, modified, and finally removed. The entire process culminates in the central validation box. This final verification, labeled as step 5, is the crucial proof of a successful cleanup. It shows that an attempt to get the resource after deletion correctly results in a 404 not found error. This visual story illustrates a complete, self-cleaning test workflow, where not only is the resource's lifecycle tested, but its final absence is also proven. Step-by-step solution: Postman collection, using JavaScript. Disclaimer: always test code in a non-production environment. Our flow begins with a post request to create a post. The test script captures the new ID for chaining, then asserts not only the 201 created status but also performs an echo validation to confirm the title and user ID in the response match what we sent. The second request uses the captured new post ID to fetch the resource we just created. The test validates that the data in the response is correct, confirming the create operation was successful. Next, we send a put request to the same endpoint with an updated title. Our test checks that the title in the response matches our new updated title, proving the update worked. The fourth request is a delete call. We write a more robust test that accepts either a 200 OK or a 204 no content status, as both are valid success responses for a delete operation in different API designs. This final, crucial step provides absolute proof that the delete worked. We attempt to get the resource one last time, and the test only passes if the server responds with 404 not found. This confirms our test has successfully cleaned up after itself. Follow-up question 1. What does it mean for an operation to be idempotent, and which of these CRUD operations should be? Answer. An idempotent operation is one that can be performed multiple times with the same input, and the server state will be the same as if it were performed only once. Get, put, and delete should all be idempotent. For example, deleting an item twice should have the same result as deleting it once. Post is not idempotent because calling it twice will create two new, distinct resources. Follow-up question 2. In some systems, you do not hard delete data. What is soft deletion and why would you use it? Answer. Soft deletion is a strategy where you do not actually remove the record from the database. Instead, you mark it as inactive with a flag like is_deleted, true or a deleted underscore at timestamp. This is used for auditing, data recovery, and maintaining historical data integrity. In that case, our delete request would likely be a patch to update that flag, and our verify step would be to get the item and assert that its deleted flag is now true. Follow-up question 3, curveball. What happens if the update step in this flow fails? How would you prevent the delete step from running and reporting a misleading error? Answer. That's an excellent question about workflow control. In the test script of the update request, I would add a conditional check. If my assertions fail, I would explicitly stop the collection run by calling postman.setNextRequest, null. This command tells the collection runner to halt immediately, preventing it from proceeding to the delete step and ensuring the test report accurately shows the failure at the point where it occurred. What the interviewer is really looking for. End-to-end thinking. Can you design a test that covers a full user workflow, not just isolated API calls? State management. Do you demonstrate a solid ability to capture data from one response and use it throughout a multi-step flow? Knowledge of HTTP verbs and idempotency. Do you correctly apply post, get, put, delete and understand their properties? Test atomicity. Do you understand the importance of cleanup and verification to ensure tests are reliable and non-destructive? Workflow orchestration. Do you know how to sequence requests and control the flow programmatically? Your turn, extension. The API at https://json placeholder.typico.com/comment supports CRUD operations, but you need a post ID to create one. First, get a valid post ID from the /posts/1 endpoint. Then, perform a full CRUD cycle on a comment associated with that post ID. Create it, read it, update its body, delete it, and finally, verify its deletion. As a final, more advanced verification, make a GET request to /comments post ID = 1 and write a test to assert that the ID of your deleted comment is no longer present in the returned array. Transition, Part 2 to Part 3, Intermediate to Advanced. Great work, you've now mastered the intermediate skills that many testers never go beyond. But to truly stand out in interviews and in your career, you need to step into advanced territory. In Part 3, we'll explore OAuth, mocking APIs, performance baselines, advanced reporting, and integrating external data. This is where you shift from a test executor to an automation problem solver. Let's move into advanced API testing. Part 3, Advanced Skills, Challenges 11 to 16. Welcome to Part 3 of the series. Here, we enter the advanced stage of API testing. You'll learn how to securely test APIs with OAuth, simulate unavailable endpoints with mocks, baseline performance, and generate professional reports that hiring managers expect. You'll also connect APIs with external data sources, proving you can handle real-world enterprise workflows. This part is all about demonstrating depth, showing that you don't just know the basics, but can handle the complex challenges enterprises face every day. API Testing Challenge 11, OAuth 2.0, the Proactive Refresh Flow. The interview task: design a proactive, self-healing authentication test. A senior interviewer presents a system-level challenge. Our platform uses an OAuth 2.0 flow with short-lived access tokens that expire every 15 minutes, but we also issue long-lived refresh tokens. I need you to design a stateful Postman collection that can run for hours without manual intervention. Your solution must be proactive. Before making a protected request, it should check if the access token has likely expired. If so, it should refresh the token first. It must also be reactive. If a 401 still occurs, it must trigger a refresh and then retry the original request. Prove this dual strategy, self-healing mechanism works. The visual anchor: proactive versus reactive token management. This diagram visualizes a sophisticated, two-tier defensive strategy for managing authentication tokens in a resilient test suite. The process begins with the first tier, a proactive check at the top. Before any API call is made, it asks, is date.now token_expiry? If the token has expired, yes, the flow diverts to the orange refresh tokens action preemptively. If the token is still valid, no, the flow proceeds along the green happy path to the main action. 1. Run protected request. After the request is made, the second tier of defense engages, a reactive check. The diamond asks, response is 401. If not, the flow continues to the green, test passed, 200 OK, box, completing the happy path. However, if an unexpected 401 error occurs, yes, the flow diverts down the orange recovery path, leading to the same shared refresh tokens action. From the refresh tokens box, the self-healing loop completes as the orange arrow labeled run request points back to the beginning, retrying the protected request with the new token. Finally, the diagram includes a critical failure path. If the refresh tokens action itself fails, the red arrow points to the ultimate fallback, trigger full login, preventing an infinite loop. Step-by-step solution: Postman proactive workflow, using JavaScript. Disclaimer: always test code in a non-production environment. The masterpiece strategy begins here. After the initial login, we do not just store the tokens. We capture the expires underscore in duration, calculate the future timestamp of expiration in milliseconds, and save it. This enables our proactive checks. This logic lives in the pre-request script tab of our protected request. Before the request is even sent, it checks if the token has expired. If it has, we skip the doomed request entirely and jump straight to the refresh token step, saving time and preventing an unnecessary API error. This is our safety net. If the proactive check passed, for example, due to clock skew between client and server, but the request still failed with a 401, this reactive logic in the tests tab catches the failure and triggers the same refresh flow. We have now covered both proactive and reactive scenarios. The refresh request completes the self-healing loop. After successfully getting and storing the new tokens and their new expiry time, we use setNextRequest parentheses to redirect the runner back to the getProtectedData request to retry it. This ensures the original user action is completed successfully. Follow-up question 1. What happens if multiple parallel requests detect an expired token simultaneously? How do you prevent a thundering herd of refresh requests? Answer: that's a critical concurrency problem. In a real application, you would not let each failed request trigger its own refresh. The standard solution is to implement a singleton pattern or a locking mechanism. The first request to detect the expiry would lock the token refresh process and send the request. All subsequent requests that fail during this time would be queued or would wait for a promise to resolve with the new token. Once the new token is fetched, it is shared with all waiting requests, preventing a storm of redundant calls. Follow-up question 2. What are the security risks if a refresh token never expires? Answer: A non-expiring refresh token represents a permanent backdoor to an account. If it is ever compromised, an attacker has indefinite access until the user manually revokes it or changes their password. This creates a massive attack window. That's why modern security standards recommend that refresh tokens either have a reasonably long but finite lifetime, for example, 30 to 90 days, or, even better, use refresh token rotation to invalidate the previous token on each use, drastically reducing the impact of a token leak. Follow-up question 3. Why is the authorization code grant type considered the gold standard for OAuth 2.0? Answer. It is the most secure because it follows a three-legged flow that never exposes the user's password to the client application. The user is redirected to the trusted authorization server to log in, the server sends a temporary, one-time use code back to the client via the browser, and then the client's backend securely exchanges that code for the actual tokens. This separation of concerns is the core principle of OAuth delegation and protects against many types of attacks. What the interviewer is really looking for. Proactive versus reactive design. Can you think beyond simple failure recovery and design a system that preemptively avoids failure? Concurrency and race conditions. Do you consider system-level issues like thundering herds that arise in real-world, high-traffic scenarios? Deep security principles. Do you understand the why behind token rotation, expiry, and secure grant flows? Architectural trade-offs. Can you articulate the difference between client-side and server-side logic and their respective security implications, for example, storing tokens? Your turn. Extension. Implement a maximum retry safety mechanism. In the get protected data request, use a counter variable in the pre-request script. If the request fails with A401, increment the counter. In the refresh token logic, check this counter. If it exceeds a threshold, for example, 2 retries, use postman.setNextRequest, null, to halt the collection and prevent an infinite loop, which could be caused by a misconfigured server that keeps returning 400 ones even after a refresh. Real-world capstone angle. This dual proactive/reactive model is how enterprise-grade systems ensure resilience. The next level is to add metrics. How would you measure the effectiveness of this system? You could log every proactive refresh versus every reactive refresh. A high number of reactive refreshes could indicate a systemic problem, like client/server clock skew, allowing you to architect a better, more efficient solution instead of just constantly reacting to failures. This is the difference between testing a feature and owning system reliability. API Testing Challenge 12, File Integrity, the Upload and Download Cycle. The interview task. Validate the round-trip integrity of a file. A senior interviewer wants to test your handling of non-JSON data. We have a feature for users to upload and download their profile avatar. I need you to design an end-to-end test for this. You will post a sample image file, avatar.png, which is 15,024 bytes, to /users/123/avatar using multipart/form data. Then, you will make a second GET request to the same endpoint to download it. Your tests for the download request must be comprehensive. Assert that the content type header is correct, that the content disposition header suggests the correct file name, and most importantly, that the size of the downloaded binary data exactly matches the original file's size, proving no data corruption occurred. The visual anchor, the file round-trip integrity check. This diagram visualizes the end-to-end process of testing file integrity through a round-trip API interaction. On the left, the process begins with an original file. A prominent callout box lists its known properties, baseline, the file's name, type, and exact size. This establishes the ground truth that our test will validate against. In the center, 2 arrows show the round-trip transaction with the API server. The first arrow, labeled 1. Post, upload, shows the file being sent to the server. The second arrow, 2. Get, download, shows the file being retrieved from the server. On the right, the validation stage is depicted. The downloaded binary data from the server is subjected to an inspection, represented by the magnifying glass icon. The result of this inspection is a checklist with 3 green check marks, signifying that the downloaded file's properties perfectly match the original baseline, confirming a successful and uncorrupted round trip. Step-by-step solution, Postman requests, using JavaScript. Disclaimer: always test code in a non-production environment. For the upload, we configure the request body to use form data, the standard for sending binary file data. In Postman, we add a key named file, set its type to file, and select our local avatar.png. Our first check on the download request is the content type header. This is critical because it tells the client how to interpret the binary data it is receiving, in this case, as a PNG image. This senior-level check validates the content disposition header, which is a formal signal to the client suggesting a file name for saving the file. It proves the API is providing complete and correct metadata. This is the core integrity validation. We use a robust method to get the exact size of the binary response in bytes, compatible with different Postman environments. We assert that this size is identical to our known original file size. Any mismatch indicates data corruption during the round trip. Follow-up question 1. What happens if 2 users upload files with the same name, avatar.png, at the same time? How would you test that the system avoids collisions? Answer: a well-designed system should never use the client-provided file name for storage. Upon upload, it should generate a unique identifier, like a UUID or a hash of the file content, as the new file name to prevent collisions. I would test this by having 2 parallel test runs, using Newman, for instance, upload files with the same name. I would then inspect the response from both uploads, asserting that they return 2 different, unique URLs for the stored resources, proving the collision was avoided. Follow-up question 2, beyond size and type, how would you test that important metadata, like EXIF data in a JPEG photo, survives the upload process? Answer: that's a great question about data preservation. Some upload processors aggressively strip metadata to reduce file size. To test this, I would use a library, like exif.js in the prerequest script or a local script, to read key EXIF fields, like camera model or date taken, from the original image. After downloading the file and the test, I would use the same library to parse the downloaded binary and assert that those specific EXIF fields are still present and have the same values. Follow-up question 3, curveball: we have verified the file size. How could you verify the file's content integrity with cryptographic certainty? Answer: the gold standard is a checksum. Before uploading, I would use a crypto library in the prerequest script to calculate a SHA-256 hash of the local file. A robust API would do the same upon receiving the file and return this hash, often in the eTag header. My test would then assert that the eTag value from the API response matches the hash I calculated locally. This is a far more reliable check than a size comparison and proves that the file's content has not been altered by a single bit. What the interviewer is really looking for. Beyond JSON, can you handle different data formats and understand the specifics of multipart/form data requests? HTTP protocol mastery: do you know the purpose of critical headers like content type and content disposition? System-level thinking: do you consider real-world problems like concurrency, race conditions, and metadata preservation? Data integrity concepts: can you articulate a strategy for proving a file has not been corrupted, moving from simple, size, to advanced, checksums, validation? Your turn, extension. Create a test for a CSV file round trip. Create a simple data.csv file with a few rows. Upload it to a hypothetical/reports endpoint. Then, download it and write a test that goes beyond metadata. In your Postman test script, parse the raw text of the downloaded CSV response and assert that it contains a specific, expected value from one of the cells, for example, a specific user's name. This proves you can validate the file's internal content, not just its size. Real-world capstone angle. This round-trip integrity testing is critical for any system where data fidelity is non-negotiable. Think of financial applications where users upload bank statements, healthcare platforms for medical images, X-rays, MRIs, or legal systems for signed documents. A single bit of data corruption in these files could have catastrophic consequences, making this type of validation a core pillar of quality assurance. API Testing Challenge 13, Chained Microservices, Validating a Distributed Business Workflow. The interview task: validate an end-to-end order fulfillment flow. A senior interviewer describes a core business process. Our e-commerce platform is built on microservices. When a customer places an order, it triggers a distributed transaction. I need you to write a test that validates this entire flow. 1. First, a post to the orders service creates an order and returns an order ID with a status, pending. 2. Next, a post to the payment service, using the order ID, processes the payment. 3. Finally, a post to the shipment service, also using the order ID, arranges for shipping. Your test must not only check for successful responses but must also verify that the order's state is correctly updated after each step. You must prove that the final status of the order is shipped. Crucially, you must also implement a X correlation ID header to trace this single transaction across all three services. The visual anchor, the distributed transaction and correlation ID. This diagram visualizes a distributed transaction across three independent microservices, each shown as a distinct silo. The flow is unified by a single correlation ID, a unique digital passport generated at the start and passed as a header in every API call. Solid arrows represent direct service calls, while dotted arrows show the side effect state changes propagating back to the order service. This visual thread makes the complex interaction traceable, which is essential for debugging in a distributed environment. The final green checkmark validates the business workflow's successful completion. Step-by-step solution: Postman business workflow, using JavaScript. Disclaimer: always test code in a non-production environment. The masterpiece strategy begins at the collection level. We use Postman's native crypto.randomuid function to generate a unique correlation ID. This ID will be our digital passport, attached as a header to every request to trace the entire transaction. After calling the payment service, we add a traceability check. We assert that the response from the payment service itself includes the correct order ID, confirming that it processed the correct transaction. This is a critical validation step. After the payment service is called, we do not assume success. We go back to the source of truth, the order service, and query the order again. We assert that its status has now changed to paid, proving the side effect of the payment call was successful. Follow-up question 1. What if two payment requests for the same order ID arrive at the same time? How would you test that a user is not charged twice? Answer: this is a test for idempotency. The payment service must be designed to handle this. It should use an idempotency key, often the order ID itself or a unique transaction ID, to ensure that only the first request is processed. To test this, I would run two identical post/payments requests in parallel using Newman. I would then assert that the first request returns a 200 OK, while the second returns a different code, like a 429 conflict or 200 OK but with a body indicating the payment was already processed. Finally, I would check the order's transaction history to confirm only one charge was recorded. Follow-up question 2. A correlation ID is great for logs. How would you test that this ID is being consistently emitted in other observability pillars, like metrics and traces? Answer: that's a fantastic question that goes beyond basic API testing. To validate this, I would need access to the observability platform, like Datadog or Prometheus. After my test run, I would query the platform using the correlation_ID I generated. I would assert that, 1. A distributed trace exists that is tagged with my correlation ID and shows spans from all three services. 2. Key business metrics, like orders_created or payments_processed, are emitted with a label or tag matching my correlation ID. This proves that our traceability is consistent across logs, traces, and metrics. Follow-up question 3, deep dive. This test assumes a synchronous flow. How would your strategy change if the shipment service was triggered by an asynchronous event from a message queue? Answer: my strategy would shift to testing for eventual consistency. I could no longer call the get/orders endpoint immediately and expect a shipped status. Instead, I would implement polling. My test script would loop, querying the get/orders/order ID endpoint every few seconds for a defined timeout period, for example, 30 seconds. The test would only pass once it observes the status change to shipped, validating the asynchronous workflow while also measuring its latency. Follow-up question 4, architectural. If the shipment fails after payment, how does the system handle this? What is this pattern called? Answer: this is handled by the saga pattern. Since we cannot use traditional database transactions across microservices, we use a series of compensating transactions to undo previous steps. If shipment fails, the shipment service would publish a shipment failed event. The payment service, listening for this event, would then trigger a refund for that order ID. Testing the saga pattern means validating these failure recovery paths, trigger a failure at step n, then assert that the compensating transactions for steps n1, n2, etc., were all successfully executed. What the interviewer is really looking for. Distributed system mindset. Do you see this as a single business transaction spread across services, not just 3 API calls? Understanding state and side effects. Can you design tests that validate the indirect effects one service call has on another? Observability and debugging patterns. Do you know what a correlation ID is and why it is a cornerstone of microservice architecture? Architectural awareness. Can you discuss advanced concepts like eventual consistency, idempotency, and compensating transactions, sagas? Your turn, extension. Now, test the failure path of this workflow. Simulate a payment failure by sending an invalid credit card number to the post/payments request. A well-designed system should not leave the order in a pending state. Instead, it should trigger a compensating action. Your final verification step, get/orders/order ID, should now assert that the order's status has been updated to payment_failed or cancelled. Real-world capstone angle. This is not just testing APIs, this is validating a core, revenue-generating business process. A failure in this chain for an e-commerce giant could mean millions in lost revenue and a logistical nightmare. The ability to test, trace, and debug these distributed workflows is one of the most valuable skills for a senior engineer in any modern, cloud-native company. API Testing Challenge 14, Performance Assertions in Functional Tests. The interview task, validate an API against a performance SLA. A senior interviewer gives you a scenario that blends functional and non-functional requirements. Our search autocomplete endpoint, get/products or search, Q equals, has a strict service level agreement, SLA, that response times must be under 200 milliseconds for typical requests to ensure a fluid user experience. I need you to write a single Postman test that validates two things simultaneously. First, that the search returns a valid, non-empty array of products, and second, that the request completes within this 200 milliseconds performance budget. How would you implement this check, and more importantly, what are its limitations? The visual anchor, the dual-gauge quality check. This diagram visualizes a dual-pronged approach to validating a single API response by checking both its content and its speed. On the left, an API server issues a single API response. This response acts as the source for two separate validation checks, as shown by the branching arrows. The top path leads to a green functional validation gauge. This box confirms the data's integrity with a simple checkmark, indicating that the content is valid. The bottom path leads to a blue performance validation gauge. This box uses a speedometer metaphor to measure the response time. The needle, pointing to 150 milliseconds, is clearly within the green zone of the dial, which is marked as being under the 200 milliseconds threshold. This confirms the response was fast enough. The visual demonstrates that a truly high-quality response must satisfy both conditions, the functional check and the performance check must both be in the green. Step-by-step solution, Postman test script, using JavaScript. Disclaimer, always test code in a non-production environment. We start by defining the performance budget as a constant. This makes the test readable and easier to update if the SLA changes, a best practice over hard-coding magic numbers directly in the test. First, we ensure the API works correctly. This robust functional check verifies not just a 200 OK status, but also that the response body is a non-empty array with the expected structure. An API that is fast but returns wrong data is useless. This is the performance check. We use Postman's built-in pm.response.responseTime property, which contains the total request duration in milliseconds. We then assert that this value is less than our defined SLA. This test will fail if the API is functionally correct but too slow. Directly addressing the interviewer's question, we explicitly state the limitations. This shows a senior-level understanding that this test is a valuable but limited smoke test, not a replacement for dedicated performance testing. Acknowledging these trade-offs is a key indicator of experience. Follow-up question 1, you mentioned this is not performance testing. Can you elaborate on the difference? Answer, absolutely. This is a performance assertion within a functional test, a baseline check for a single user under no load. True performance testing, or load testing, is a separate discipline that uses tools like K6 or JMeter to simulate hundreds or thousands of concurrent users. Its goal is to measure system behavior under stress, analyzing metrics like throughput, latency distribution, P95, P99, and error rates to find bottlenecks and ensure scalability. Follow-up question 2, what factors could cause this test to be flaky, failing intermittently? Answer, flakiness in this test is common and usually stems from environmental variance. The response time includes network latency between my machine and the server load at that exact moment, and potential database query fluctuations. That's why these checks are most reliable when run in a stable, controlled environment, and why we often look at performance trends over time rather than reacting to a single failed test. Follow-up question 3, curveball: the actual SLA is 200 milliseconds at the 95th percentile, P95. Your test only checks one response. How would you design a test in Postman to approximate a P95 validation? Answer, that's an excellent question that requires data collection. I would use the Postman collection runner to execute this request 100 times. In the test script for each iteration, I would push the pm.response.responseTime into a globally scoped array. In the teardown script for the very last request, I would process this array, sort it numerically, find the value at the 95th index, for example, sorted times 94, and then assert that that specific value is below 200 milliseconds. This is an advanced technique that provides a much more statistically significant result. What the interviewer is really looking for. Understanding of NFRs: do you recognize that performance is a non-functional requirement that can be validated alongside functional ones? Pragmatism and context: can you articulate the crucial difference between a performance assertion, smoke check, and a real performance test, load test? Acknowledging limitations: do you proactively identify the weaknesses and trade-offs of your own testing approach? Statistical thinking: do you understand concepts like variance, percentiles, P95, and why a single data point can be misleading? Your turn, extension. Parameterize your SLAs for better reusability. In your Postman environment, define two variables, SLA_default_ms, set to 200, and SLA_large_payload_ms, set to 500. Create a second request that fetches a larger payload, for example, using a limit equals 100 parameter. Modify your test scripts for both requests to read the SLA value from these environment variables instead of hard coding them. This demonstrates a more scalable and maintainable test design. Real-world capstone angle. In the world of e-commerce, every 100 milliseconds of latency can correlate to a 1% drop in sales. For financial trading platforms, milliseconds can mean millions of dollars. Integrating performance assertions directly into your functional CI/CD pipeline acts as an early warning system. It will not replace dedicated performance engineers, but it will catch costly regressions the moment they are introduced, long before they impact customers and the bottom line. API Testing Challenge 15, Mocking and Contract Testing, Unblocking Parallel Development. The interview task: design a mocking strategy to enable a blocked team. A senior interviewer lays out a common organizational problem. The mobile team is ready to build a new user dashboard, but the backend team will not have the required /user/ID /dashboard endpoint ready for another 2 sprints. As the lead test engineer, you are tasked with unblocking the mobile team today. First, create a high-fidelity mock server in Postman that returns a realistic response, validated against a JSON schema to prove it is contract compliant. Then, in your explanation, I want you to clearly state the limitations of this one-sided mocking approach and propose how you would evolve it into a more robust, bidirectional contract test using a tool like PACT. The visual anchor: the contract as a bridge. This diagram perfectly illustrates the core concept of using an API contract as a bridge to unblock parallel development. At the top, the scenario is established. A consumer team and a producer team are separated by a blocked development gap. Positioned centrally as the solution, the orange API contract acts as the bridge and the single source of truth. From this contract, 2 parallel workstreams flow downward. The left path shows a mock server being generated, enabling the consumer team to develop and test their application. The right path shows the real API being built by the producer team. Both teams work independently and in parallel, guided by the same contract. Finally, both work streams converge at the bottom into a single, green integration success checkpoint. This visualizes the ultimate benefit of this strategy. Because both teams built against the same blueprint, their work is guaranteed to connect perfectly. Step-by-step solution: Postman mock server, using JavaScript. Disclaimer: always test code in a non-production environment. Before any mocking, we establish the source of truth, the API contract. This consists of a formal JSON schema defining the structure and a concrete example response. This contract is the negotiated agreement between the front-end and back-end teams. Using this contract, we configure a mock in Postman. We create a request that matches the target endpoint and save our JSON example as the expected response. Postman then hosts this example at a unique URL, effectively creating an instant, contract-compliant mock API. This is a crucial step. We do not just consume the mock, we write a test against the mock to validate the mock itself. The key assertion validates that the mock's response conforms to the schema, ensuring the mobile team builds against the correct data structure. Directly addressing the interviewer's prompt, we explicitly state the limitations of this approach. Acknowledging that this is a valuable but imperfect, one-sided solution shows a senior-level understanding of engineering trade-offs and sets the stage for proposing a more robust solution like PACT. Follow-up question 1: You have stated the limitations. So why is a tool like PACT considered a true contract testing solution? Answer: PACT solves the core limitation by being bidirectional. The consumer's tests generate a PACT file, the contract, which is then shared. The producer's CI/CD pipeline runs a verification step that replays requests from the PACT file against the real API. If the producer makes a breaking change, their build fails. PACT enforces the contract on both sides, creating a feedback loop that guarantees the consumer and producer will not diverge. Follow-up question 2: In a real project, who owns the API contract? The consumer or the producer? Answer: This is an architectural question. The contract is a negotiated agreement and is CO-owned. Typically, the consumer will initiate the discussion by proposing a contract that meets their needs. The producer then reviews, refines, and approves it. Once agreed, the contract becomes a shared artifact in a central repository, and both teams are responsible for adhering to it. It is a collaborative process, not a top-down mandate. Follow-up question 3, curveball: how would you handle a stateful mock? For example, if the mobile team needed to post new activity to the mock and then get the updated dashboard. Answer: Postman mocks are stateless by default, but you can simulate statefulness by creating multiple examples for the same endpoint. You can configure Postman to return a specific example based on request parameters or headers. I would create a default dashboard example and an updated dashboard example. The mobile team would first get the default. After their post, they would get the dashboard again but with a special header like xMockState, updated. I would configure the mock server to return the updated dashboard example only when it sees this header, simulating a state change. What the interviewer is really looking for. Shift-left mindset: do you think about testing early in the lifecycle to prevent defects and unblock teams? Producer or consumer dynamics: do you understand that modern development is about managing dependencies and contracts between services? Pragmatism and tool choice: can you articulate the trade-offs between a simple mock, Postman, and a robust contract testing framework, Pact? Architectural influence: do you see testing's role as not just validating code, but as a mechanism for enforcing design agreements and improving collaboration? Your turn, extension. A new requirement has come in: the dashboard must now include an account status field which can be active, suspended, or deactivated. Create a dashboard v2.json schema that includes this new required property, as an enum. Then, create a new mock example /v2/dashboard that returns the updated payload. Finally, explain how you would manage this version change to ensure it does not break existing consumers who are still using the v1 endpoint. Real-world capstone angle. This strategy is not just a technical trick, it is a direct accelerator for business value. In large organizations, waiting for dependencies is the single biggest cause of project delays. By using contract-driven mocking, you enable parallel development, which can shave weeks or even months off a feature's time to market. The ability to articulate this business impact, we ship features faster because we test smarter, is what defines a senior engineer.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
API Testing Challenge 16, GraphQL API Testing, the Single Endpoint Challenge. The interview task: validate a GraphQL query and mutation. A senior interviewer introduces a modern architecture. Our new platform is powered by a GraphQL API, served from a single/GraphQL endpoint. I need you to demonstrate you can test its core operations. First, write a mutation to create a new user, using GraphQL variables for the input data. From the response, capture the new user's ID. Second, write a query to fetch that specific user by their ID, but be efficient, only request their name and email fields. Your tests must validate the response data shape and correctness for both operations, proving the client is in full control of the data it receives. The visual anchor, the GraphQL query response mirror. This diagram perfectly illustrates the core principle of GraphQL, where the shape of the response is a direct mirror of the request. On the left, the GraphQL query box shows a client crafting a specific, nested request for a user's name and email. The structure of this query defines the exact data shape the client wants. The central arrow shows that this entire query is sent in a single post request to the universal/GraphQL endpoint. On the right, the JSON response box shows the data returned by the server. Crucially, its structure exactly matches the query's structure. The colored, dashed lines visually connect each field from the query to its corresponding key in the response, providing an undeniable visual proof that the client received precisely what it asked for, with no extra or missing data. This demonstrates how GraphQL eliminates overfetching by design. Step-by-step solution, Postman GraphQL requests, using JavaScript. Disclaimer: always test code in a non-production environment. First, we define our mutation. We declare the variables it accepts, prefixed with $, and their types. Inside, we specify the create user operation and the exact fields we want back. The input data itself is passed separately in the GraphQL variables section, a best practice for reusability and security. In the mutations test script, we parse the JSON response. GraphQL data is nested under a data key. We traverse the response, data.createUser.id, to find the new user's ID and save it to an environment variable for our next request. For our second request, we define a query. We are specifically asking for the user with a given $user ID and requesting only the name and email fields. This is the core power of GraphQL. The client dictates the exact shape of the response. This is the most important assertion. Instead of just checking for what's there, we assert that the user object has exactly and only the keys, name, email. This single line provides absolute proof that the GraphQL server respected our query and we did not receive any overfetched data. It is a more robust and precise test than checking for the absence of one specific field. Follow-up question 1. What is the N+1 problem, and how does GraphQL help solve it? Answer: the N+1 problem is a classic performance issue. Fetching a list of n items, one query, and then looping through them to fetch a related item for each n queries, results in N+1 database calls. GraphQL, combined with a backend pattern called data loader, solves this by batching and caching. Data loader collects all the individual requests for related items, combines them into a single, efficient database query, for example, select asterisk from posts where user ID IN, and then distributes the results back to the correct resolvers. Follow-up question 2. What stops a malicious actor from writing a deeply nested, circular query that could cause a denial of service attack? Answer: that's a critical security concern. Production-grade GraphQL servers must have multiple layers of defense. 1. Query depth limiting, refusing to execute queries nested beyond a certain level. 2. Query complexity analysis, assigning a cost to each field and rejecting queries that exceed a total complexity score. 3. Timeouts, killing any query that takes too long to resolve. For public APIs, many also use persisted queries, where only pre-approved queries stored on the server can be executed. Follow-up question 3. Curveball: how would you approach testing a GraphQL subscription that pushes real-time updates over a WebSocket? Answer: that's an excellent question that goes beyond request response. Testing subscriptions requires a WebSocket client. In Postman, I would open a WebSocket request, connect to the server, and send the subscription query as the initial message. Then, the test becomes an event listener. I would have to trigger an event on the server, for example, by running a separate mutation request to create a post. My WebSocket test would then listen for the incoming message and assert that its payload contains the data from the mutation I just triggered. It is about testing the full event-driven flow, cause to effect to validation. What the interviewer is really looking for. Client-driven mindset. Do you understand that GraphQL's philosophy is about empowering the client to define its own data needs? Schema-first thinking. Do you treat the GraphQL schema as the definitive contract and source of truth for the entire API? Beyond syntax, can you write clean, reusable operations using variables instead of hard-coding values into query strings? Architectural awareness. Can you discuss the performance, N+1, security, query complexity, and real-time, subscriptions, implications that are unique to GraphQL? Your turn, extension. Write a more complex query that demonstrates GraphQL's power to traverse relationships and handle arguments. Using the user ID you captured, write a single query that fetches the user's name and the title of their first 3 posts, sorted by ID in descending order. Your test script should validate that the posts array has a length of at most 3. Real-world capstone angle. This is the architecture that powers the news feeds of companies like Facebook and the complex dashboards of GitHub. It allows front-end teams to innovate rapidly, adding and removing data from their views without having to file a ticket and wait for the back-end team to create a new REST endpoint. The ability to test this flexible, powerful architecture is a key skill for engineers working on modern, product-focused applications. Welcome to the capstone of our API testing interview series. You've mastered the fundamentals, chaining calls, data-driven testing, validations, and automation best practices. Now it's time to level up. In these final 4 enterprise-grade challenges, you'll step into the shoes of a real SDET working on production systems. Challenge 17, orchestrate a full end-to-end user journey, register, login, purchase, and invoice. Learn to stitch APIs into a real-world workflow. Challenge 18, build your own API testing framework in REST Assured, with base classes, utilities, and configs for scalability and reusability. This is what interviewers look for when they say, "Can you design a framework?" Challenge 19, integrate Postman plus Newman into a Jenkins CI/CD pipeline, making your API tests the quality gate that decides if code ships or fails. Shift-left testing at its best. Challenge 20, the grand finale. Step into a security tester's mindset, simulate SQL injection, fuzzing, and malicious inputs. Prove you can defend the system, not just validate it. By the end of these challenges, you won't just answer API testing interview questions, you'll demonstrate the mindset, the frameworks, and the security awareness that separate a junior tester from an automation architect. This is your graduation project. Let's dive into the capstone. API Testing Challenge 17, End-to-End User Journey, the e-commerce checkout flow. The interview task, validate the entire customer purchase journey at the API layer. A hiring manager presents you with the final, most critical test. I need you to build a complete, end-to-end API test that simulates our core business function, a customer purchasing a product. This is our primary smoke test that runs on every deployment. Your test must orchestrate a sequence of calls that, 1. Registers a new user. 2. Logs that user in to capture an authentication token. 3. Uses that token to purchase a specific product. 4. Retrieves the final invoice. Crucially, your assertions must go beyond 200 OK. You must prove data integrity across the entire journey, verifying that the user ID from registration and the product details from the purchase step are correctly reflected on the final invoice. The visual anchor, the user journey pipeline. This diagram, titled the Session Integrity Pipeline, visualizes a complete, stateful user journey through an e-commerce transaction, focusing on data integrity. The journey begins on the left with an anonymous user, who enters the pipeline at the 1. Register station. This first step generates the initial piece of state, a user ID. The diagram then visually shows this session object growing at each subsequent step. At the 2. Login station, an auth token is added. At the 3. Purchase station, an invoice ID is added, completing the session's data collection. The entire process culminates at the 4. Final validation station on the right. Here, the test performs its most critical checks. As shown by the colored, dashed lines, it traces data from the final invoice back to its origin points in the session. It asserts that the user ID on the invoice matches the one from registration and that the total price is correct, proving that data integrity was maintained across the entire multi-step business workflow. Step-by-step solution, Postman business workflow, using JavaScript. Disclaimer: always test code in a non-production environment. The masterpiece strategy begins before any request. We use a collection-level script to set a universal correlation _ID for traceability and to define the entire user session and product data up front. This ensures our test is rerunnable and self-contained. In the first step of our journey, we register the user with the credentials we defined earlier. The test script then captures the newly created user ID from the response and saves it to an environment variable, which is the first piece of our evolving user session. The second step uses the same credentials to log the user in. Here, we capture the critical auth token from the response. This token is the key that will unlock the protected, transactional endpoints in the rest of our flow. This is the core business transaction. We send an authenticated request using our auth token to purchase the specific product ID _to_ by defined at the start. The successful response gives us the invoice ID, which is the final piece of state needed for our validation. This is the payoff. We do not just check if the invoice exists, we perform deep validation by retrieving all collected state, user ID, product ID, price, and asserting that the final invoice correctly reflects this data. This proves that our entire business workflow maintains data integrity from start to finish. Follow-up question 1. How would you test a negative path in this flow, such as a product being out of stock at the purchase step? Answer: would use a data-driven approach. I would add a specific product ID to my test data that is known to be out of stock in the test database, for example, prod out of stock. When the test runs with this data, I would change the assertions in the purchase step to expect a 409 conflict or similar error code, and validate that the response body contains a specific error message like item is out of stock. The flow would then stop, proving the system handles business rule failures gracefully. Follow-up question 2. This is a great end-to-end test. How would you design a test suite to ensure this does not break other, more isolated functionalities? Answer: this end-to-end test is the top of the testing pyramid. It would be part of a larger suite. Below it, I would have many more focused integration tests that test smaller interactions, for example, just login and profile fetch, and a large base of unit tests for individual service logic. The E2E test validates the critical business path, while the integration and unit tests provide broader coverage and pinpoint failures more quickly. You need all three layers for a robust strategy. Follow-up question 3. Curveball: why is this API-level end-to-end test often more valuable than an equivalent Selenium or Cypress UI test? Answer: because it is faster, more reliable, and provides earlier feedback. A UI test for this flow might take 30 to 60 seconds and could fail due to a minor CSS change or an animation not loading. This API test runs in under a second and is completely isolated from the UI, so it only fails if the core business logic is broken. By running this in our CI/CD pipeline on every commit, we get high-confidence validation of our most critical revenue stream much earlier and more reliably than we ever could with a UI test. What the interviewer is really looking for. Business process validation: do you think in terms of user journeys and business outcomes, not just API endpoints? Stateful system testing: can you design a test that manages and validates state as it changes across a multi-step transaction? Data integrity consciousness: do you have the foresight to check that data remains consistent from the beginning of a workflow to the very end? Strategic test design. Can you articulate the value and trade-offs of API-level E2E tests compared to other forms of testing, UI, integration? Your turn, extension. Add another layer of business logic to this flow. Before the purchase step, add a new request, post/coupons or apply with a body like, coupon code, save 10. This should return a discount amount. Capture this value. Then, in the final invoice validation, update your business logic assertion to verify that the invoice.total amount equals the original product price minus the captured discount. Real-world capstone angle. This test represents the apex of automation maturity, orchestrating APIs as business workflows, not isolated endpoints. For any online business, this user-can-buy product flow is the most important one in the entire system. Having a fast, reliable, and comprehensive API test that validates this journey is the highest value automation you can build. It provides a high-confidence, low-cost safety net that protects the company's core revenue stream. API Testing Challenge 18, API Test Automation Framework, rest assured the architectural showcase. The big picture. In this capstone challenge, we're moving from writing one-off API tests into designing and running a production-ready API automation framework. Think of it as building your own testing engine, one that's scalable, reusable, and CI/CD friendly. This challenge has two key parts, each focused on a different dimension of automation maturity. Part A, building the framework, the architecture. Here, we roll up our sleeves and design the core layers of a scalable framework using Java plus Rest Assured. We'll structure the code into clean, reusable layers, config layer, externalizes environment details, config.properties. Base layer, defines reusable request or response specifications, headers, base URL. API client layer, wraps REST calls in business-friendly methods, create user parentheses, get user parentheses. Test layer, keeps tests clean and declarative, focusing on business flows, arrange to act to assert. The takeaway, tests stop looking like HTTP scripts and start reading like business scenarios, making them easy to maintain across hundreds of microservices. Part B, running the framework, the orchestration. Once the framework is in place, we need to execute it reliably in CI/CD pipelines. This is where orchestration tools come in, TestNG Suite, testing.xml controls test execution, smoke, regression, parallel runs. Jenkins file, automates build and test execution on every code change. Dockerfile, containerizes the whole setup, ensuring tests run consistently across environments. The takeaway, the framework doesn't just exist on your laptop, it becomes a plug-and-play testing service integrated into enterprise CI/CD pipelines. Why this matters? By mastering both framework architecture, Part A, and execution orchestration, Part B, you'll have the skills to design maintainable frameworks, run them at scale in real pipelines, and demonstrate SDET-level thinking in interviews and real projects. This is the point where you shift from being a test executor to a test architect. The visual anchor, the anatomy of a scalable API test framework. This diagram, titled From Framework to Pipeline, illustrates the two critical dimensions of a mature test automation strategy, a well-designed framework and its integration into a continuous delivery pipeline. The left panel, Framework Architecture, depicts the software's structure as a series of distinct, color-coded layers. At the top is the tests layer in green, followed by API clients in blue, the base or core in orange, and the config, models and utils foundation at the bottom. The downward arrows indicate that each layer depends on the one below it, enforcing a clean separation of concerns. The right panel, Pipeline Orchestration, shows how this framework is executed. It features a series of tools, the TestNG Suite, to define what tests to run, Jenkins, as the automation server, and Docker, to provide a consistent runtime environment. The pipeline culminates in reports and metrics, which provides the final pass or fail verdict. Connecting these two panels is the crucial CI/CD integration arrow. This visualizes the core message of the challenge. A clean, scalable framework is designed to be plugged into an automated pipeline to enable reliable, continuous testing at scale. The interview task: design a scalable API automation framework. An engineering manager challenges you. Our organization has over 200 microservices, and our current Postman scripts are becoming brittle and hard to maintain at scale. I need you to design and build a production-ready API test automation framework from scratch using Java and REST assured. Your design must promote reusability, maintainability, and be ready for CI/CD integration. Then, as a proof of concept, implement a clean, readable test for the /users CRUD endpoint. How to ace the interview: your thought process. 1. Deconstruct and acknowledge. This is a classic and essential system design challenge for a test engineer. The key requirements are scalability, reusability, and maintainability. This means we must avoid putting everything in the test methods themselves. Instead, we need a layered architecture with strong separation of concerns. 2. State your architectural plan. I will design a multi-layered framework. The base layer will handle configuration and the reusable REST-assured client setup. On top of that, I will build an API abstraction layer with client classes for each service endpoint, like User API Client. This layer will hide all the HTTP logic. The final layer will be the tests themselves, which will be clean, readable, and focused only on the business logic, using a clear arrange act assert pattern. I will also include a data factory for generating test data and POJOs for type-safe data handling. 3. Narrate the why as you build. As you describe each file, explain its architectural purpose. Here is the base test.java class. Its job is to set up a reusable request specification once. By doing this here, we ensure that every single test in the framework automatically inherits the correct base URL, content type, and logging. If we need to change our timeout settings, we only change it in this one file, and it applies everywhere. This is the foundation of a maintainable framework. Here is our part: building the framework, the architecture. The framework files, an architectural overview. 1. pom.xml, the project's blueprint, defining all dependencies, REST assured, testng, etc. 2. config.properties, an external file for environment-specific data like the base URL. 3. configloader.java, a utility to read the configuration file. 4. basetest.java, a foundational class to create a reusable REST-assured client specification. 5. user.java, a plain old Java object, POJO, to model the user data. 6. user API client.java, an abstraction layer that contains methods for interacting with the /users endpoint. 7. testdatafactory.java, a utility for generating dynamic, random test data. 8. usertests.java, the actual test class, containing the clean and readable test methods. Here is the project blueprint, pom.xml. Disclaimer: always test code in a non-production environment. This is the core dependency for our framework. It brings in the entire REST-assured library, which provides the fluent, BDD-style syntax for writing API tests in Java. We use testng as our test runner. It provides powerful features like annotations, @test, @beforeclass, assertions, and the ability to run tests in parallel. Jackson is a high-performance library for serializing Java objects into JSON, for request bodies, and deserializing JSON back into Java objects, for response validation, which is essential for working with POJOs. Here is the environment config, src/test/resources/config.properties. Disclaimer: always test code in a non-production environment. This file externalizes our configuration. By storing the base URL here, we can easily point our entire test suite to a different environment, for example, QA, staging, without changing a single line of code. Here is the config loader utility, src/test/java/com/example/config/configloader.java. Disclaimer: always test code in a non-production environment. We implement this as a singleton. This ensures that the config.properties file is read from the disk only once, no matter how many times the configuration is needed across the framework. This public method provides a clean, type-safe way for other parts of the framework to access the base URL property without needing to know the implementation details of how it is loaded. Here is the foundation: src/test/java/com/example/core/base-test.java. Disclaimer: always test code in a non-production environment. The @beforeclass annotation from TestNG ensures that this setup method is run only once before any tests in a class are executed. This is the perfect place to configure our shared client. This is the heart of reusability. We create a request specification that all tests will inherit. It sets the base URL from our config, specifies that we will be sending JSON, and adds filters to automatically log every request and response, which is invaluable for debugging. Here is the data model: src/test/java/com/example/models/user.java. Disclaimer: always test code in a non-production environment. This is a POJO, plain old Java object. The @data annotation from Lombok automatically generates all the boilerplate code, getters, setters, toString, etc., keeping our model clean and readable. This class allows us to work with user data in a type-safe way. Here is the API abstraction layer: src/test/java/com/example/api/user-api-client.java. Disclaimer: always test code in a non-production environment. This class inherits from base test, which means it automatically gets access to the shared request spec we configured earlier. This is a key design pattern for reusability. This method abstracts away all the rest-assured logic. It takes a user object, sends it as the body of a post request, and returns the full response. The test layer will call this clean, business-focused method instead of writing raw HTTP code. Here is the data generator: src/test/java/com/example/util/testdatafactory.java. Disclaimer: always test code in a non-production environment. This factory method generates a unique user object every time it is called. Using a UUID ensures that our tests are self-contained and will not conflict with each other if they are run in parallel. Here is the test layer: src/test/java/com/example/tests/user-tests.java. Disclaimer: always test code in a non-production environment. The test class also extends base test, giving it access to the shared configuration and ensuring the setup parentheses method runs before these tests. The @test annotation marks this method as a TestNG test case. The method name clearly describes the business scenario it is validating. This is the beauty of our layered architecture. The test itself is incredibly clean. It uses the test data factory to arrange the data and the user API client to act on the API. There is no raw HTTP code, making the test's intent perfectly clear. We use AssertJ for our assertions, which provides a fluent and highly readable syntax. Here we validate the status code, the data echoed back from the API, and the presence of a server-generated ID. Part B: making the framework production ready. In this section, we're stepping beyond just writing tests, we're making them production ready by embedding them into a CI/CD pipeline. To do this, we need 3 orchestration layers. 1. TestNG Suite XML, defines what tests run and how they're grouped. 2. Jenkins file, defines when and how to test in the pipeline. 3. Docker file, guarantees a consistent runtime environment so the framework runs the same everywhere. Here is the orchestration layer 1, the TestNG Suite, testing.xml. Disclaimer: always test code in a non-production environment. This XML file orchestrates our test runs. The parallel equals classes attribute tells TestNG to run different test classes in parallel, which is a key strategy for speeding up CI/CD builds. Here, we explicitly define which test classes are part of this suite. This allows us to create different suites for different purposes, for example, smoke, regression, sanity, without changing any Java code. Here is the Jenkins file orchestration layer 2, the CI/CD pipeline, Jenkins file. Disclaimer: always test code in a non-production environment. This is the core execution stage in our CI pipeline. It uses Maven to compile the framework and then run the tests defined in our testing.xml suite file. This command is how automation is triggered on every code change. The post block is for teardown and reporting. We use the JUnit publisher to parse the XML test results, which allows Jenkins to track test trends and failures. We also archive the HTML report so the team can easily view the results. Here is the Docker file orchestration layer 3, the containerized runtime, Docker file. Disclaimer: always test code in a non-production environment. We start from an official Maven image that includes the full JDK. This provides a clean, predictable environment for compiling our Java code. This demonstrates a best practice, the multi-stage build. The first stage, build, uses a large image with Maven to compile everything. The second, final stage starts from a lightweight JRE image and only copies the necessary compiled artifacts. This results in a much smaller, more secure final container. The CMD instruction defines the container's default command. When the container runs, it will directly execute testng, using the compiled classes, dependencies, and our testing.xml suite file to run the tests. Follow-up question 1. Your framework is great for one service. How would you scale it to handle 200 microservices? Answer: would scale it horizontally by adding new API client packages. Each microservice would get its own API client, POJO models, and tests package, for example, com.example.api.orders, com.example.models.orders. The core framework, base test, config loader, remains unchanged. We would then use testng suite files to create targeted test runs for specific services or end-to-end flows, ensuring the test suite remains organized and manageable. Follow-up question 2. How would you add rich, visual reporting to this framework? Answer: I would integrate a dedicated reporting library like Allure. This involves adding the Allure testing dependency to the pom.xml and configuring the Maven Surefire plugin to use an Allure listener. Then, I can annotate my test methods with @step, @description, and @feature. After a test run, Allure generates a beautiful, interactive HTML dashboard with detailed request or response logs, step breakdowns, and historical trends, which is far superior to standard testng reports. Follow-up question 3. Curveball: how would you manage test data that needs to exist in the database before a test runs, like a specific user with a known subscription type? Answer: that's a precondition problem best solved by not relying on existing data. The best practice is to make tests self-sufficient. I would create a @before method setup step that uses the API itself to create the required data, for example, register the specific user, assign the subscription. Then, a corresponding @after method step would tear down that data by calling the delete endpoint. This ensures tests are atomic, can be run in any order, and do not pollute the test environment. What the interviewer is really looking for. Architectural thinking: can you design a system with clear layers and separation of concerns? Software engineering principles: do you apply concepts like DRY, do not repeat yourself, abstraction, and configuration management? Scalability and maintainability: do you have a plan for how this framework will grow without becoming a mess? Ecosystem awareness: do you understand how a test framework fits into the larger DevOps ecosystem of Maven, testng, Jenkins, and reporting tools? Your turn, extension. Apply the framework's architecture to a new domain. Implement the necessary components for the /posts endpoint. This will involve creating a post.java POJO, a post API client.java class with methods for CRUD operations on posts, and a posttests.java class to validate the full lifecycle of a blog post. This will prove you can extend the framework's design pattern to cover new services. Real-world capstone angle. This framework is not a theoretical exercise, it is a scaled-down version of what professional software development engineers in test, SDETs, build and maintain in top-tier tech companies. The ability to move beyond simple scripts and architect a robust, scalable automation solution is the single biggest differentiator between a tester and a test automation engineer. Demonstrating this thought process proves you are the latter.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
CI/CD integration with Newman and Jenkins, the automated quality gate. The big picture. In this capstone challenge, we move our testing from a manual, on-demand activity to a fully automated, integral part of the software delivery lifecycle. We are building an automated quality gate, a safety net that runs on every single code change, automatically preventing bugs from ever reaching production. This is the essence of shift-left testing. Instead of finding bugs late in the process, we are building a system to catch them moments after they are created. Mastering this skill is what transforms a test engineer into a true guardian of production quality. The interview task: build a CI/CD quality gate for an API. A DevOps lead presents you with a critical task. We have a Postman collection that serves as our regression suite for the /order service. I need you to integrate this into our Jenkins CI/CD pipeline. Your solution must define a new staging tests stage that runs after the application is deployed to our staging environment. This stage must execute the entire Postman collection using Newman. Critically, if any API test fails, the entire pipeline must stop immediately and send a failure notification. If all tests pass, the pipeline should proceed. How to ace the interview, your thought process. 1. Deconstruct and align with DevOps principles. This is a perfect task for demonstrating a DevOps mindset. The goal is not just to run tests, but to create a fast, reliable feedback loop for the developers. The key is to treat our test suite as pipeline as code, just like the application itself. I will use a declarative Jenkins file to define the stages and make the process transparent and version controlled. 2. State your technical plan. My plan involves 3 artifacts. First, the Postman collection itself, which contains the tests. Second, a Postman environment file to manage the base URL for staging, separating configuration from the tests. Third, and most importantly, the Jenkins file. This pipeline will have 3 stages: checkout, deploy to staging, and the run API tests quality gate. For the test stage, I will use Newman, the command line runner for Postman, and I will be sure to use the bail flag to stop the run on the first failure, ensuring a fail-fast approach. 3. Narrate the why and the value. As you describe the solution, focus on the business impact. Here in the Jenkins file, you can see the post block where I configure reporting and notifications. This is crucial. When a test fails, we do not just fail the build, we immediately archive the HTML report and send a Slack notification to the development channel. This closes the feedback loop in minutes, allowing the developer who just committed the code to see exactly what broke and why, directly from the CI/CD system. The CI/CD artifacts are automation in action. 1. Orders API tests.postman_collection.json, the Postman collection containing our API tests. 2. Staging.postman_environment.json, the environment file with variables for the staging environment. 3. Jenkins file, the pipeline as code script that defines and orchestrates our entire CI/CD process. The visual anchor, the CI/CD pipeline with an automated quality gate. This diagram illustrates the complete story of a CI/CD pipeline, powerfully separating the strategic why from the technical how. The top panel, the why, shows the business workflow. It follows a standard software delivery process. A developer's commit is built and then deployed to staging. Here, it hits the crucial API test gate, represented by a traffic light. If the tests pass, the process continues along the green path to promote to production. If they fail, the red path signifies the build is stopped. The bottom panel, the how, reveals the technical mechanics that power this gate. It shows a Postman collection being executed by the Newman CLI command line tool, which is in turn run by the Jenkins pipeline automation server. The most important feature is the dashed arrow connecting the two panels. It shows that the technical execution happening in the Jenkins pipeline is what provides the signal to the API test gate, determining whether the light turns green or red. This visual perfectly demonstrates how a simple Postman collection evolves into a critical, automated quality control point in an enterprise delivery pipeline. Artifact 1. The Postman collection, orders API tests.postman_collection.json. Disclaimer, always test code in a non-production environment. The collection is designed for CI/CD by using a base URL variable. This allows the same set of tests to be run against different environments, dev, staging, prod, simply by changing the environment file. This line in the test script for the create request demonstrates a chained workflow. It captures the ID from the response and saves it as an environment variable, making it available for the subsequent get request. Artifact 2, the Postman environment, staging.postman_environment.json. Disclaimer, always test code in a non-production environment. This file separates configuration from the tests. It defines the specific base URL for our staging environment. In a CI/CD pipeline, we can have multiple such files, for example, dev.json, prod.json, and choose the correct one at runtime. Crucially, we define a placeholder for the API_key. We never commit real secrets to version control. The actual value will be injected securely by the Jenkins pipeline at runtime. Artifact 3, the pipeline as code, Jenkins file. Disclaimer, always test code in a non-production environment. This stage is our quality gate. It explicitly runs after the deployment to staging, ensuring we are always testing the most recent version of the code in a realistic environment. This is the best practice for handling secrets. It tells Jenkins to fetch the credential with the ID, staging API key, from its secure credential store and inject it into an environment variable named staging_API_key. The failure block in the post section ensures that if the pipeline fails, we take specific actions. This example shows how you would configure a Slack notification, providing immediate feedback to the development team with a direct link to the test report. Follow-up question 1. How do you securely manage the API_key in Jenkins so it is not checked into the Jenkins file or the repository? Answer: the best practice is to use the Jenkins Credentials Manager. You store the API key as a secret text credential within Jenkins, which encrypts and stores it securely. The Jenkins file then references this credential by its ID using the withCredentials block. This injects the secret as an environment variable into the build container at runtime, so it is never exposed in logs or committed to source control. Follow-up question 2. What is the advantage of running these Newman tests inside a Docker container within the Jenkins pipeline? Answer: the primary advantage is consistency and portability. A Docker container bundles the application, Newman, and all its dependencies, like Node.js, into a single, immutable image. This guarantees that the tests run in the exact same environment on a developer's laptop, the Jenkins agent, and any other machine. It completely eliminates the "it works on my machine" problem and makes the CI/CD pipeline far more reliable and easier to manage. Follow-up question 3. Curveball: your tests pass, but a recent deployment caused a significant performance degradation. For example, P95 latency went from 200 milliseconds to 800 milliseconds. How would you evolve this pipeline to catch that? Answer: that's a fantastic question about integrating non-functional testing. I would evolve this into a performance quality gate. I would add a new, parallel stage to the Jenkins file that runs a small, targeted load test using a tool like K6. The K6 script would run for a short duration, for example, 1 minute, against the key endpoint. Crucially, it would define thresholds, for example, HTTP_REQ_duration, P95, 250. If the P95 latency exceeds 250 milliseconds, K6 exits with an error code, which would automatically fail the Jenkins pipeline. This adds a performance safety net to our functional one. What the interviewer is really looking for. DevOps and shift-left mindset: do you see testing as an integrated part of the delivery pipeline, not a separate phase? Automation maturity: can you articulate a strategy for running tests unattended, handling configuration, and reporting results automatically? Security consciousness: do you instinctively know not to check in secrets, and can you explain the correct way to manage them in a CI/CD context? Reliability and consistency: do you understand the value of tools like Docker for creating reproducible build and test environments? Your turn. Extension: add a parallel stage to your Jenkins file named contract tests. In this stage, run a different Newman collection. You can create a simple one that validates the API's schema against a stored contract, similar to challenge number 15. This demonstrates your ability to orchestrate multiple types of test suites, regression, contract, within the same CI/CD pipeline, each acting as its own specialized quality gate. Real-world capstone angle: this is the skill that separates a Postman user from a DevOps-aware test engineer. In modern software companies, the ability to embed automated quality checks directly into the CI/CD pipeline is non-negotiable. This automated quality gate provides an incredibly fast feedback loop to developers, reduces the manual testing burden, and acts as the last line of defense for production stability. Mastering this flow proves you can be trusted to own the quality of a service within a high-velocity engineering team. CI/CD integration with Newman and Jenkins, the automated quality gate. The big picture, from tester to guardian. This is the final capstone, the boss battle. We are now moving beyond testing for what works and into the adversarial mindset of testing for what breaks. Our goal is no longer just to validate business logic, but to actively try to breach the system's defenses before a real attacker does. This challenge is anchored in the principles of the OWASP API Security Top 10, focusing on vulnerabilities like injection and security misconfiguration. For this final test, you are not a user, you are the red team. Your mission is to prove the API is not just functional, but resilient and secure. The interview task: harden the API by simulating malicious attacks. A CISO, Chief Information Security Officer, joins the final interview panel and raises the stakes. Your team has proven the business logic is sound. Now, I need you to prove you can think like an attacker. Your task is to harden our APIs by simulating two common, real-world attacks against our /products or search endpoint. First, attempt a basic SQL injection attack to see if you can bypass the query logic. Second, run a fuzzing test by sending a barrage of unexpected and malformed data. Your validation is not for a 200 OK, your goal is to prove that the system blocks these attacks safely, returns a controlled error, like a 400 bad request, and never crashes or leaks sensitive information like a stack trace. How to ace the interview, your thought process. 1. Deconstruct and align with security principles. This is a critical challenge that tests a security-first mindset. My goal is to validate the API's input validation and error handling robustness. I will be looking for two main failure modes. Does the API let the malicious query through, or does it fail in an insecure way by crashing, 500 error, or leaking internal error details? A secure API should do neither. 2. State your technical plan. I will structure this as two distinct attack scenarios using a data-driven approach in Postman. For the SQL injection, I will have a data file with a classic payload like or 1 is equal to 1. For the fuzzing test, I will use another data file with a range of malformed inputs, an oversized string, a null value, special characters, and a payload with the wrong data type. The key to both tests will be the assertions. I will explicitly check for a 400 bad request status and assert that the response body does not contain common database error strings like SQL syntax or exception. 3. Narrate the why and the value. As you present the solution, focus on the defensive value. This fuzzing loop is a simple but powerful way to automate robustness testing. By throwing a variety of unexpected data at the endpoint, we are testing the resilience of the input validation layer. A 500 internal server error on any of these inputs would be a critical failure, indicating an unhandled exception that an attacker could exploit. By asserting for a consistent 400 bad request, we prove the API is gracefully rejecting invalid data as designed. The security artifacts, our defensive test suite. 1. SQL injection payloads.csv, a data file containing classic SQL injection strings. 2. fuzzpayloads.csv, a data file with a variety of malformed and unexpected inputs. 3. securitytests.postman_collection.json, a Postman collection with two data-driven requests, one for each attack vector. The visual anchor, the API as a guarded castle gate. This diagram, titled API Security, the Castle Gate Defense, uses a powerful metaphor to illustrate the core principle of API security testing. On the left, a series of attacker inputs are aimed at the system. These inputs are color-coded to distinguish between a legitimate request in green and two malicious payloads in red, representing attacks like SQL injection and cross-site scripting. In the center, a prominent shield acts as the API's defensive layer, the castle gate, which includes components like a web application firewall, WAF, and robust input validation. The diagram clearly shows this shield in action. The green arrow from the legitimate input is allowed to pass through, while the red arrows from the malicious payloads are explicitly blocked. On the right are the protected systems, representing the backend database and services. The successful green arrow reaches this backend, resulting in a green checkmark. This signifies that the system processed the valid request correctly while remaining completely unharmed by the blocked attacks, proving the castle's defenses are effective. Artifact 1, SQL injection payloads, SQL injection payloads.csv. Disclaimer, always test code in a non-production environment. Our first data file defines the malicious inputs for our SQL injection test. Each row contains a classic injection string and a descriptive name for clear reporting. This payload is the quintessential SQL injection. It attempts to alter the where clause of a SQL query to always be true, potentially bypassing authentication or returning all records in a table. Artifact 2, fuzzing payloads, fuzzpayloads.csv. Disclaimer, always test code in a non-production environment. This data file contains a variety of unexpected and malformed data types. Fuzzing is a technique used to discover unhandled edge cases in an application's input validation logic. This test case is particularly important. We are sending a complex data type, a JSON object, where the application is expecting a simple string. A robust API should gracefully handle this type mismatch with a 400 bad request, not a 500 internal server error. Artifact 3, the security collection, securitytests.postman_collection.json. Disclaimer, always test code in a non-production environment. This request is designed to be data-driven. The SQL_payload, a variable, will be replaced by a value from our SQL injection payloads.csv file on each iteration when run with the Postman collection runner. This is a key security assertion. We are not checking for 200 OK. Instead, we assert that the API responds with a controlled client-side error code. A 500 would be a failure, but a 400 proves the validation layer is working. This is a critical information leakage test. Even if the API fails, it must fail securely. We inspect the raw response body to ensure it does not contain common database error strings, which would give an attacker valuable information about our system's architecture. The primary goal of our fuzzing test is to check for robustness. This single, powerful assertion proves that for every piece of malformed data we sent, the server handled it gracefully and did not crash with a 500 internal server error. Follow-up question 1, your fuzzing list is short. How would you scale this to cover thousands of permutations in a real CI/CD pipeline? Answer, this Postman approach is a great starting point for regression. To scale it, I would integrate a dedicated security tool into a separate, nightly pipeline. I would use an open-source tool like OWASP Zap or a commercial DAST scanner. The CI/CD job would proxy the API traffic through Zap, which would automatically perform a much more comprehensive active scan, including a massive library of fuzzing strings and attack vectors, and then fail the build if it finds any high-priority vulnerabilities. Follow-up question 2. What is the difference between this type of security testing and a formal penetration test? Answer, this is automated security regression testing. It is designed to be run frequently and automatically to catch known types of vulnerabilities, like SQL, basic XSS, that might be introduced during development. A penetration test is a much more in-depth, often manual, and time-boxed engagement performed by a specialized security expert. They use creativity and a deep understanding of the system's business logic to find complex, novel vulnerabilities that automated scanners would likely miss. Follow-up question 3, curveball you have tested for SQL injection. What is Broken Object Level Authorization, BOLA, and how would you write a test for it? Answer, BOLA is the #1 vulnerability on the OWASP API Top 10. It occurs when a user can access data they should not be able to. For example, user A can access user B's invoice. I would test for it by creating a stateful test. First, I would log in as user A and capture their token. Then, I would log in as user B and capture their token and their unique invoice ID. The critical test would be to make a request to get /invoices/user_B_invoice ID, but using user A's token. If the API returns a 200 OK, it is a critical BOLA vulnerability. The expected result is a 403 forbidden or 404 not found. What the interviewer is really looking for. Adversarial mindset, do you think beyond the happy path and actively try to break the system in malicious ways? Risk-based thinking, do you understand common, high-impact vulnerabilities, like OWASP Top 10, and know how to test for them? Defensive validation, do you know how to write assertions that prove a system is failing securely, for example, checking for 4xx codes and no information leakage? DevSecOps awareness, can you articulate how these security checks can be automated and integrated into a CI/CD pipeline to shift security left? Your turn, extension. Implement a test for Broken Object Level Authorization, BOLA, as described in the curveball question. Create a test flow where you log in as two different users, you can mock this or use different credentials. Capture an order ID that belongs to user A. Then, using the authentication token for user B, attempt to make a GET request to /orders/user_A_order ID. Write an assertion to prove that the API correctly returns a 403 forbidden or 404 not found status, blocking the unauthorized access. The grand finale, from tester to guardian. This challenge completes your transformation from a tester into a guardian of the system. In today's world, every company fears a data breach. Functional bugs can cost money, but security vulnerabilities can destroy trust and reputation. By showing that you can embed this adversarial, security-first mindset into your API testing strategy, you prove you're not just validating features, you're actively protecting the business, its revenue, and its users. That is the mark of a true software development engineer in test and a leader in quality engineering.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links. For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.